I also have the capability of doing some powerful spatial analysis on the web with a web browser. Many people are placing their mapped data with their GISs on the internet these days, and one of the most powerful sites out there is the nationalatlas.gov. Nationalatlas.gov. National Atlas is a compendium, an assortment, a resource containing hundreds of different data layers from the U.S. Geological Survey, from NOAA, from the Bureau of Land Management, from the U.S. Forest Service, and others. Let's use the National Atlas to investigate climate. If I go ahead and turn on the average annual precipitation and redraw the map, I can see some patterns. Let's zoom in on the continental United States right now. What patterns do you notice? Well, for one thing, it seems apparent that the precipitation over in the eastern and the southeastern United States is a little higher than the Midwest and the West. Let's go ahead and click on the map key so we can see what the units are and also what the colors mean. The average annual precipitation in inches averaged from 1961 to 1990 each year. So we can see that these areas generally are wetter than the Midwest and the West, but there are some notable exceptions. Namely, the northwest coast, the Cascade Range, has some of the highest values of all. Why is that? Is this along the lines of what you expected or not? And if not, why not? What factors influence average annual precipitation? What are some factors going on here? Landforms, air masses, the jet stream. There are lots of things that go into climate for the United States, or for any region. I've now turned on the shaded relief and zoomed to Washington State to investigate a little more deeply. I can see the Cascade Range here, stretching from north to south along the west central part of the state. I also see this large area of flatter terrain toward the southeastern part of the state. I'm going to go ahead and turn on the average annual precipitation once more. And I can see that that flattish area in the southeast part of the state is definitely drier. Let's go ahead and turn on the map key again. It's so much drier, in fact, that it's only around 40 or 50 inches per year, ranging to just over 140 for some of these areas. So it's pretty amazing to see the difference. Obviously, the terrain has a lot to do with it, right? The air masses are wet from flowing across the Pacific Ocean. They dump their precipitation against the Cascade Range because it's the first high land mass that these air masses encounter, leaving little precipitation to fall on the eastern slopes of the Cascade Range. There's lots more that goes into it, but that's one of the spatial patterns that we can detect quite easily with a web-based GIS like the National Atlas. Another resource that shows very well the power of using GIS on the web is a site called This Dynamic Planet. It's jointly published by the U.S. Geological Survey and the Smithsonian Institution. This dynamic planet shows us plate boundaries, earthquakes, volcanoes, and even impact craters. It also allows us to do things like look at the rate of plate movement over time. If I zoom in here on the Pacific Plate, I see that this part of the Pacific Plate is moving at 85 millimeters per year. Knowing the rate of plate movement allows me to do things like calculate real problems. For example, how long will it be before Los Angeles is at the same latitude and longitude as San Francisco? Or notice the direction of plate movement over time has changed here in the middle of the Pacific Ocean. Hawaii is this long string of islands, as we know, but then after that there is a long string of seamounts that do not break the surface of the ocean. And over time, as the hot spot underneath the Pacific as the crust has moved over the hot spot, we get this long trail. Have your students compute, based on the current rate of plate movement, at which time in history was this point that I'm pointing to right now experienced? In other words, when was this spot over the hot spot? So when did it change direction from being primarily a north-south movement to what we have today, where the actual plate is moving in a northeast or northwesterly direction? We can look at the relationship of earthquakes, plate boundaries, and volcanoes. For example, I can see that the North American plate and the Cocos plate here are moving against each other, creating this subduction zone. Lots of earthquakes and volcanoes occur along those subduction zones, including this one along the western boundary of Mexico and the countries in Central America. We also have impact craters here. So here's the impact along the Yucatan that is believed to have ended the Cretaceous period. If I scroll up here to Canada, I see another very interesting crater. If I zoom over here to Quebec, I see the Manicouagan crater right in the middle of the province, as you can see right here. This is what this crater looks like. Here's what it looks like. Manicouagan crater is identifiable primarily because it has this large ring lake that encompasses the outer boundaries of the impact crater. And here's the Rift Valley in East Africa. So through this dynamic planet and other web GIS sites, we can see that we can do some pretty powerful spatial analysis just on the internet. I encourage you to do that.